this talk is that I originally developed this talk for the networking community, and so you're going to see that a little bit in the intro to these slides. So one way to see this talk is me explaining Crossroads work to networking people, and now I'm coming back and explaining the networking view to the Crossroads people, which has been one of the funnest parts of this center is sort of straddling that boundary. And of course, all of the work that I'm about to talk to you about, of course, was the collaboration between lots of people, Crossroads PIs, as well as other faculty and scientists, including folks from Intel and Microsoft and many other collaborating institutions. So for those of you who know a lot about the evolution of networking, you've probably seen something that looks like this before. If we consider the evolution of network programming over the last few years, one way to look at it, which I'll call the P4-centric way, is a progression as follows. First, in networking, we had these fixed function ASICs that were running our packet switching. They were carrying packets and deciding where to direct them based on longest prefix matching, and all of this was hard-coded into the hardware designs. These things were somewhat configurable, but not really very programmable, and so researchers and engineers complained that they couldn't really extend these things very well. Then came the rise of software-defined networking. And software-defined networking was slightly more programmable through a new interface called OpenFlow. And OpenFlow allowed us to customize what was happening in the switches using a series of max action operations. And the state of the art in software-defined networking today is manifested in PISA or Tofino or programmable match action switches. And these devices are programmed using a somewhat expressive language that is still tailored to packet processing called P4. Now, all of this buildup is somewhat for naught because I'm about to talk to you about all of the things that don't fit into the P4 world. So for things that didn't fit into the P4 world, things that were doing a little bit more than switching and steering packets, we threw all of this packet processing back on general purpose servers. We didn't have any hardware customization whatsoever. And many important networking applications still rely on general purpose servers because they simply don't fit into the P4 model that has been customized for packet processing. So this is my bread and butter and my background. These are applications like deep packet inspection, where we do intrusion detection and prevention or exfiltration monitoring, looking into the contents of packets and deciding whether or not they're malicious. Things like transport termination, we're running TCP or TLS front ends to offload the cryptographic operations and maintain highly stateful application state in the network. These are applications that are doing anomaly detection or machine learning over traffic, or highly stateful tasks like WAN optimization. So all of these are very common in our networks today, but we've stuffed them off onto general purpose servers because our fancy networking hardware does not support them. Unfortunately, I'm going to argue today that these network applications are, like many other network applications we've optimized for, not very well matched to the architecture of general purpose servers. So here's the part where I'm going to be slandering most of you. So remember that I originally gave this talk to a networking audience. So I told them that computer architects don't know anything about networks. And I apologize in advance for this. But how traditional computer architects see server architectures, first of all, they think that software invokes the network and not vice versa. And by they, I mean we. In every class I ever took, we had this mental model that the CPU really has to be involved in every action going on, and that what's going on in the CPU is really the most important thing to look at in order to determine how the CPU should act. This statement is a little fuzzy, so I want to give you an example. Consider the memory stack. The memory stack implicitly assumes that the most important data, the data that matters, is data that the CPU already has, because the CPU is important. I/O was an afterthought until the introduction of DDI/O. So DDI/O is an optimization that allows the NIC to push packets directly into cache after they arrive off of the network. And so this was an implicit recognition in the hardware that the network knows something that the CPU doesn't. And the network has some control over what's going on in the server without consulting the CPU. So This is a very modest step. I think that RDMA is an even more radical push in this direction towards recognizing that the NIC has the right to invoke action on the server without touching the CPU. Another assumption is that the CPU is really a one-stop shop for processing. When data arrives at the NIC, it has to cross this 10,000-mile chasm to get to the CPU, and that 10,000-mile chasm is PCIe. And today, as we move to having more and more accelerators and GPUs, if we have data coming in off the network, we go over this 10,000-mile chasm to go to the CPU, and then go across the 10,000-mile chasm again to get somewhere else. PCIe is often even constructed in a tree with the CPU sitting at the root because everything else is subsidiary. A final assumption is that I/O is rare, that the majority of compute cycles will be spent doing non-networking things. Think of all the optimizations we learn about the design and processors memory hierarchy. We're always focusing on optimizing things that are already there. And it's only recently that we've started to think about more and more optimizations to speed up getting things to and from the wire. And yet in I/O-driven applications, like the network functions I referenced, data is continually arriving off the network demanding to be processed. Every arriving packet is implicitly a demand to invoke functionality. Modern applications may also involve multiple compute platforms, GPU, disk, accelerators. So this pushes the CPU into this incredibly strange situation where the CPU is an orchestrator, receiving all the data coming off the network and then triaging it across other processor cores, shipping it off to disk or sending it to an accelerator. Sometimes in the networking literature, you see this referred to as an I/O core. So we're wasting the CPU just doing all the network stuff. So if we think about the assumptions I laid out about the server overall architecture, these assumptions break down when it comes to applications that I refer to as I/O driven. So instead of software invoking the network, it's really the case that networking is invoking the software. Instead of the CPU being a one-stop shop, processing might involve multiple applications. Data is moving around across these things. And finally, I/O is common and frequent, not for all applications, but for this class of applications. There's a mismatch about the amount of data coming across the wire and how much compute is going on. So I started using this phrase I/O-driven applications without really telling you what I meant. I gave you some examples about these networking applications, the things that I said were my specialty. But there are actually a wider range of applications that have these three properties that I lined up here. It's not just network functions, but it's also key value stores or lightweight classifiers, web servers and caches, streaming data analytics. All of these things have this property that the network is invoking functionality. They're often multi-platform processing that is different accelerators, and they have lots and lots of I/O relative to the amount of compute that's being performed. So it's not just these network functions or middleboxes that are mismatched with the traditional application model. It's not all applications that are mismatched, but there's definitely this large class of application, I/O-driven applications. Now, for a long time, a lot of clever software designs masked this mismatch. And general purpose servers have done just fine supporting I/O-driven applications up until the last couple of years. Here's some of my favorite papers from network functions virtualization. All of these are doing clever software tricks to help the server keep up with the deluge of data coming on across the wire. And so for a good while, this worked out pretty well. When I used to review and read papers, the evaluation sections were incredibly boring. You would see some graph that looked like this. Throughput is on the y-axis, and then some system configuration is on the x-axis, and then there was a red line showing the network line rate that the system could achieve. And the graphs all looked like this. Everybody just topped out the link rate, and we were done. There was no more data to process. The server had done its job. But then line rates grew, and we weren't always getting there. And now for many applications, the gap between the line rate is how much data is coming off of the wire and what the server is actually able to compute can be quite wide. So let me give you some specific numbers. Here I'm showing time on the x-axis and the state-of-the-art link rate on the y-axis. It's worth noting, Moore's law, that affects your CPU. It does not affect optical networking. That stuff is still going up at very, very fast rates. As a matter of fact, I drew this graph with a line of 100 gigabits per second as the state-of-the-art line, but many of the data center operators that we work with are moving to 400 gigabits per second, and they're planning for a terabit per second coming off of a single wire. So here's the line rate going up over time. And here's the throughput you can achieve just doing a simple ping pong application that is packet in, packet out with a 3.1 gigahertz processor core and Intel E810 100 gigabit per second NIC. We're able to sustain only about 40 gigabits per second. And if I add 2 processor cores, we're already in the domain of sublinear speedups. We don't go to 80 gigabits per second, we only go up to 60. And keep in mind, this is a fake application. This is just a packet in and out. This is just ping-ponging. We're not doing any work. For an application like the Snort IDS, this is one of those devices that looks inside of packet bodies and determines whether or not there's an attack. Even with 16 3.1 gigahertz cores, we top out at 20 gigabits per second. So the law of the land in all of that beautiful work I showed you that was masking the problem with CPU parallelism will save us. We've seen this slide 1,000 times across every domain of computer systems. It remains true in networking. CPU parallelism is done. It's not saving us. We need more clever architecture. So here's an example, once again, from the Snort IDS, telling us on the y-axis the number of CPU cores that we would need to sustain zero loss 100 gigabit per second throughput, given different traffic traces running through the system. We would need somewhere between 77 and 667 processor cores attached to that one wire. And of course, more cores is a bad idea. It costs more money, more energy, and more rack space. As an aside, a thing that drives me absolutely nuts in the networking literature is that sometimes systems don't evaluate this, and so they propose some new system that looks faster, but actually is way more expensive or it eats up a ton of power. So always be skeptical of a proposal for new hardware systems that don't evaluate these things. So, okay, that brings us back to our core general purpose server. It's creaking away under this deluge of network data. And so today I want to talk about a vision that has slowly been developing over the past couple of years through the Crossroads Center. And that's about the changes in our software and our hardware that we need to make to moving towards designing an I/O-driven server. This is a server that is derived from general purpose servers, but that is optimized for these I/O-driven applications. Today in data centers, we already see some servers that are, for example, storage optimized for high storage applications. And we envision that there's a future class of servers that are highly optimized for serving I/O-driven workloads. Now, I'm not going to present only work here that has come out of the Crossroads Center, and that's because I believe that there is a wide ecosystem of work in the systems and networking community that is starting to touch on this idea and fill in our vision of an I/O-driven server in general. So I'm going to tell you about 3 projects that have come out of the Crossroads Center: Pegasus, Enso, which is actually going to appear this summer, and Kopi, which appeared last year. But I'll also touch on some really exciting work going on in other groups of computer systems from folks like Simon Peter, Tom Barbette, Dion Kostic, Danielle Yu, Kyung-Soo Park, Irene Zhang, etc. Okay, so I/O-driven server. We have this beautiful idea that we're going to adapt our general purpose servers to supporting these applications that are driven by I/O. What I am going to argue is that to design an I/O-driven server, we need to re-architect the hardware and the software to treat the NIC rather than the CPU as the controller for network processing. And the enabling technology that allows us to do this, where we couldn't do it 10, 20 years ago, the rise of SmartNICs, FPGA-based switches, DPUs, and Intel's IPUs. Now, some of the first software systems to handle SmartNICs just identified them as an accelerator. They're like, oh, there are all these accelerators. Let's try this new accelerator. It's NIC, but it's smart. And I think that programmable NICs aren't important just because of the type of compute that they propose, although I really love FPGAs. I think there's this sort of macro architectural or system integration perspective that we should be careful about looking at. And that is this. When you have programmability on the NIC, whether it's an FPGA or just an x86 processor or something else, you can invert the control of the server. They allow us to reorient both the hardware and the software to explicitly optimize I/O by placing the NIC in control of how and where data is processed. And this leaves the CPU free to do what it's actually designed for, which is servicing the application-specific code. So most of you have already heard about Pegasus absolutely ad nauseum. But I want to talk about Pegasus once again, because Pegasus is really where we started thinking about I/O-driven control. So Pegasus targets signature-based intrusion detection and prevention, signature-based IDS taking rules like the one I'm showing here. And in software, resolving whether or not a flow matches a rule can be decomposed into the following stages. First, the packets arrive and are parsed to identify Ethernet, IP, and then the TCP headers. Then there's the TCP reassembler. Then a pattern matcher looks for exact matches in the contents of the packet payload. These are exact match strings that tell us things that are associated with attacked. And then finally, we send the packets to a full matcher that performs regular expressions and a couple of other checks before making a final determination as to whether or not a packet or a flow represents an attack. The Pegasus team was not the first team to apply FPGAs to accelerating intrusion detection. But traditionally, they stuck to this model that the CPU was king. The CPU was in charge. And so data would come in, it would hit the CPU, which would do the majority of processing. And then the FPGA would be this worker node on the side that might accelerate one or two tasks. Typically, it was accelerating something like string matching or the regular expressions. But the key thing that Pegasus does that enables its orders of magnitude speedups is that it flips this. The FPGA is doing all of the process except the full match, and most of this is fairly boilerplate Ethernet parsing TCP, and then some application-specific functionality, which is just string matching. The NIC performs all processing except the full match. That's the regular expression processing and a few other checks. And so Pegasus, by adopting this architecture, is able to do a massive amount of highly parallel filtering over the traffic before shipping it up to the CPU. And it turns out that we can identify 95% of innocent packets as truly innocent right there on the FPGA, bypassing the CPU entirely. A mere 5% of packets wind up traveling to the CPU. Furthermore, the FPGA has done another level of filtering that I'm not showing here. It's identified that many of the signatures definitely do not match this packet, and therefore that the CPU does not need to check them. Of those 5% of packets, they typically only are being sent to the CPU alongside 1.1 rules to check out of an original 35,000 rules. So all of that is to say the FPGA is doing a bunch of work, and it's leaving the CPU to do so little. Only about 5 gigabits per second goes to the CPU. And from the perspective of Pegasus, the CPU is a regular expression accelerator. So this is a kind of silly graph, but it is instructive. Between Snort and Pegasus, Pegasus uses orders of magnitude fewer processor cores. The filtering on the FPGA does a lot of work. But to see whether Pegasus is really a better deployment choice than Snort, we have to consider the cost of the FPGA. And that's why evaluating things like power or financial cost is really important. Using multiple CPUs can be a good choice if it's cheaper or if it uses less power. But in the case of Pegasus, we see that Pegasus uses about an order of magnitude less energy than the CPU-based approach by adopting the FPGA. So an average about 30 times less. And using public pricing schemes, we estimate that it would cost about 1/3 as much to run Pegasus as Snort running on software. So stepping up from a level, let's talk about the lessons we learned from Pegasus. Some of Pegasus's gains are definitely micro-architectural. Like I said, I really love FPGAs, and they're super powerful at doing lots of fast processing in parallel. But today, I really want to focus on the macro-architectural or system integration lesson. And that is, from Pegasus's perspective, the NIC is the controller of the compute. and the CPU is doing some application-specific work. It's just the regular expression accelerator. If we extrapolate this lesson to help us envision what a server optimized for I/O would look like, we can look at the traditional offload model like this. In the traditional model, the CPU has to receive all traffic and process it, and it may choose to delegate to another accelerator. But in a network-driven architecture, acceleration might be performed inline on the NIC, like in Pegasus. Or acceleration might involve multiple accelerators, but bypass the CPU entirely. Last fall, we hosted here at CMU, Min-Lan Yu, who talked about a new project from her and her collaborators at KAIST, in which the NIC pulls data directly from disk to write out from the network, bypassing the CPU from serving video streaming content. You might also imagine the NIC shipping data directly to a GPU or some other CPU, because now the NIC is the controller orchestrating the compute. So our first task for our NIC as controller in an I/O-driven server is to give the NIC the responsibility of steering traffic to the right worker node for processing. Another lesson from Pegasus is how important it is to try and filter and reduce data. So much of that 100 gigabit per second coming across the wire can be reduced or deduplicated quickly. And this should be no surprise to those of you who have thought about data processing more broadly. For example, in big data frameworks, we spend a lot of time thinking about how to filter and deduplicate data, for example, in MapReduce and Spark workloads. And so network workloads are no different. We want to be able to reduce that stuff before it gets to the CPU and takes on the high expensive processing. In the traditional architecture, the CPU is forced to take on this big fire hose of data that it's not ready for, and it has to do any filtering on its own. This fire hose of processing not only takes up CPU cycles, but as recent work from Google and Berkeley shows, it can result in host internet connect congestion, hurting latency and throughput. By filtering on the NIC, we relieve both PCIe and the CPU from this onslaught of data, once again, letting the CPU do what it's good at, which is the application-specific processing. So like I said, this is really powerful, even though it's kind of obvious when you look at the history of large data compute. Finally, we should consider interfacing with the outside world. In Pegasus, this is the TCP reassembly and the Ethernet parsing, getting the data into the format so we can do something at the application layer. If the CPU still has to do everything, it has to do all of this boilerplate stuff. But in a network-driven world, the NIC can be responsible for interfacing with the outside, and the CPU is now truly just an application-specific worker node. It does the application-specific stuff, but now the NIC is handling the protocols, the network security, the isolation, the switching, etc. So those are our last things to push to our NIC as controller. It's easy to think of these things as offloads, and yes, these are a natural progression of our current offloads. But when you push all of this to the NIC and your application is already driven by high network I/O, you really wind up in a position where the NIC has taken charge of the whole system. There's so much left, there's so little left for the CPU, it can now use up all of those x86 cycles for easy C++ or Python programmability. Unfortunately, that's a lot of stuff. So my students have been hammering away at pieces of this back in my lab. And we published a vision piece on how to integrate this stuff into the NIC last year at HotOS. As an aside, James has been talking about this idea about the relationship between GNU and Linux. A lot of the work that we've been doing right now has been building up GNU. What are the pieces that are going to run on this NIC? But eventually we will need to develop the Linux. So what does that Linux look like? And our vision for the answer of that is something called COPY. So in the traditional kernel software network stack, if we don't have a smart NIC, what happens when data comes in off of the wire is the NIC hands data into the kernel, and then the kernel is going to copy traffic over to application-specific buffers. But for decades now, people have complained that this software design is not a good choice because of the number of copies involved and because of the cost of context switching between the kernel and the application. So over the past 10 years or so in the software world, software app hackers have decided that we're going to skip the kernel entirely, and they're going to talk directly to the NIC from the applications. This is really at the forefront of Intel's DPK. Thank you, Intel, for this lovely technology because it has enabled a huge jump in high-performance I/O-driven applications. This avoids copies and syscalls because the kernel is out of the picture. But it has a problem. And the problem is that kernel bypass makes applications hard to manage and maintain. So debugging, partitioning ports, process scheduling, QoS, all of these things that the kernel used to do for us are completely gone with kernel bypass. Here's an example of something that the software world gave up with kernel bypass. Here's Bob. And Bob is not a very sophisticated computer user, and his application is sending too much traffic. And it's not leaving enough bandwidth for the high priority database on his shared server. If Alice is a system administrator, she could say, well, I want to prioritize traffic from the database over traffic from Bob's application. And the kernel can implement that for her using something like TC. If Bob sets a weak password and his server gets compromised with a malicious web server, Alice might notice that there's malicious traffic coming out of the network. And to debug this, she might ask, well, which application is listening on port 80? She might use tools like NetStack to check all of the open sockets. These features and others are very useful, but administrators have actually given up on them when they adopt kernel bypass. And this is really problematic. A lot of companies don't adopt the performance gains of kernel bypass because they don't want to give up these features. And the problem here is that we don't have any way to interpose on the traffic. So when we follow through on this I/O-driven approach and we let the NIC take over, what we're actually doing is we can bring back control to the kernel by letting the kernel do the programming of that NIC. And now the control is not control that's living in the CPU that requires those performance overheads of bouncing in packets around. The application is talking directly to the on-path NIC that it was going to talk to anyway. And yet we're still getting all of the functionality that we want. So our proposal is called kernel on-path interposition. It's still an area that is very actively being researched in our group, and I hope to be sharing new components of it over the next couple of years. In fact, I'm going to tell you about one of the new components that's going to appear at OSDI this year in just a couple of slides. And that component is the interface between the NIC and the applications. So popping back up to the big picture again, I'd like to look forward at a bunch of open questions that we're considering here at the Crossroads Center, but that I'd also like the systems and networking and architecture community to think about jointly. One big and obvious thing is that I just outlined a ton of features, each of which are hard to implement with good performance and memory efficiency and all of those things that I want. There have been some beautiful papers in recent years on offloading software switching or TCP offload. And to get the full feature set that we want in the NIC, there's still a lot to do to develop what James calls the GNU for the COBE universe. Another broader question is how much operating system functionality should become the domain of the NIC. One question is how much scheduling should be sitting on the NIC versus scheduling running in some process on the CPU or running on the CPU. On the hardware side, throughout this talk, I've danced around a little bit about what kind of hardware we put on the NIC. As part of the Crossroads sensor, we really advocated that FPGAs play a major role in this. Through the Pegasus project, we've seen the huge power, the parallelism, and yet open programmability of the FPGA to do a bunch of sophisticated processing that PISA can't. That said, we might still want a PISA pipeline along the side. We might want more x86 processors, or we might want to harden certain features. In ongoing work in the Crossroads Center, we're actually considering which features we might want to harden as part of the COBE Center. And so I think that exactly what goes into those future IPUs or GPUs is a really important question for us to answer jointly between the applications and the architects. Another question is about the interconnect. PCIe connects the CPU to a root complex, treats other endpoints as peripherals. Should the NIC instead be at the root? How does CXL play into this world if the NIC is really the controller of the situation? I don't know. And how should the NIC communicate with other processors and platforms? platforms. So this is the last project I'm going to plug from the Crossroads Center. We have a new protocol for interacting between the NIC and the application that is designed for IO-driven applications running in the COPE world. But you don't have to have all of that to use it. The software and the hardware components are available today on GitHub, and you can check them out. So let me tell you what's special about this new protocol. In the traditional NIC to CPU protocol, and that's what it is, it's really a protocol. PCIe is just a network. There is a hardened protocol that runs in the network interface card that has remained pretty unchanged since the 90s. And this protocol is explicitly packetized, and it allocates buffers all over in memory. It assumes that you're using a memory pool model. But if the NIC is not transferring packets, maybe the NIC is doing some of your reassembly, or maybe it's doing some of your serialization, you wind up in this weird situation where you have data that you're stuffing back to look like packets before you ship it over the wire. What if we're transferring a byte stream or a series of serialized RPC requests? At best, this is awkward for programming, but at worst, I'm going to tell you that this is also terrible for performance. So Hugo, who is here in the room, has proposed an approach called Enso, where he argues that we should just use an unstructured green buffer to put whatever data we want in the buffer on the application side. And so the protocol for data transfer just needs to synchronize the head and tail pointers for this opaque data. It could still be packets that we're transferring between NIC and application, but it could be a byte stream, or it could be some sort of reassembled serialized requests. All of these things can just be put into an Enso buffer with a format that's agreed upon between the NIC and the application. The key idea is really simple, although there are a bunch of tricky details into making it work later. Well, we have a white paper if you're interested in reading more. But it turns out, like I said, that this approach isn't just sort of cleaner from a programmer's perspective. It also results in better spatial locality and hence better cache performance. It reduces the amount of metadata going across PCIe, and it saves the application from wasting cycles wrangling that data back into an application memory format. So even for raw packet data, if I'm just doing what DPDK would do for me today, Enso enables much higher I/O rates than the existing approaches. Okay, so that was a lot of case studies, and I also cited some other work going on in the field today. And that's because I really believe that the I/O-driven architecture is the convergence of a lot of great ideas that are going on both in the offloads world, but also really being enabled by work going on at Crossroads Center today. So just to recap, line rates are going up. Applications that are driven by incoming I/O are suffering. And our servers should let the NIC be the king of processing, driving what happens on the server in order to effectively triage all of this incoming data. But there's a lot left to do. Thanks for listening, and I'm happy to take questions.